Okay, hello everyone. Welcome to 130B, Quantum Mechanics. So today we are going to start a new topic about hydrogen atom. So last time we have finished our very tedious, maybe complicated discussion of angular momentum. But you can see this, the way that we are the way that we study angular momentum is not by solving any differential equation. Previously, you may have already learned about electron wave functions in a hydrogen atom, where you already see something like a spherical harmonics, and those spherical harmonics orbitals basically is also labeled by angular momentum quantum numbers. But we can see that angular momentum is actually a concept that does not require you to solve any differential equation, and you can basically use algebraic methods just by studying the commutation relation between the operators and their relations, and already can use quantum bootstrap to tell you what are the possible states and what are the possible quantum number. So we will follow the same strategy and try to solve hydrogen atom again. So differ from your conventional way of solving hydrogen atom, where you write down the Schrödinger equation and it becomes a very terrible differential equation and try to solve it with many special functions. That's not what we are going to do here. So what we are going to do today is to basically resolve the problem, but using this algebraic method again. So in order to talk about hydrogen atom, the only thing that's different between hydrogen atom and angular momentum seems to be that both of them, they have three-dimensional space rotation symmetry, but hydrogen atom also, the electrons can also move in the radius direction. It is not just a rigid body that's spinning around the nucleus. It's also has radial motion. Okay. So in order to introduce this topic in quantum mechanics, I would like to first review a little bit more about classical mechanics. So imagine that electron is not a quantum particle, it's a classical particle. Then we can also talk about the classical mechanics of hydrogen atom. Hydrogen atom is a bound state of a single electron and a single proton. And the proton is so heavy, it is much, much heavier than the electron, that the mass ratio between the proton mass and the electron mass is almost 2,000 times. Proton is almost 2,000 times heavier. So the proton essentially is pinned at the center of mass. If you have these two bodies moving around each other, and then the center of mass of the system will be remain static, right? So, but if one of the body is so heavy, then basically it's almost like the proton has no motion. So we can almost view that the proton is always at the center of mass, and the electron is moving surrounding it. And it is also the same case when you have a planet circling around orbiting around the sun, for example. So that's basically the same physics. And this corresponding orbital is also called Kepler orbital, because it is starting from these celestial motions. So now consider the electron moving in an electrostatic potential, or you can think about it as a planet moving in a gravitational potential, but it's the same kind of form, which the potential energy basically decays with the distance from with the electron-proton distance in an inverse 1/r manner. And then there is a coefficient, alpha, which is the so-called fine structure constant, which has to do with the electron charge, and then it describes the strength of the electrostatic Coulomb force in this problem. So now we can, in classical mechanics, I'm only talking about classical mechanics for now, so you can see every physical quantity, I didn't put a hat on top of it. It is not an operator yet. So in classical mechanics, we also have the concept of Hamiltonian, which basically is the energy of the system. So we only care about the motion of electron. So that's why the Hamiltonian contains the kinetic energy of the electron, where the mass here is the electron mass, and then the P here is the electron momentum. And then we suppose that the proton is at the origin of our frame of reference. So we can use this r, which is the length of this displacement vector. So this r, if I have a broad face, that is the vector version, which is the displacement vector of the electron away from the proton. But if there's this normal face, normal font, then it is basically the electron-proton distance. It's the length of the displacement, okay? So the potential energy will be inversely proportional to the distance, and then the kinetic energy will be proportional to p squared. And then you can see in this Hamiltonian, there are some parameters like electron mass, and this alpha describes the strength of the Coulomb force. So we can, in order to simplify the problem a little bit, we don't want to carry this m and alpha all the way down there in our calculation. So that's why people typically do a rescaling of r and p. So we can divide this r. Whenever we see a r in our expression, we just replace it by r over m alpha. Whenever we see a p in this expression, we just replace it by p times m alpha, because m alpha anyway is just a constant. And whenever we see an energy in our expression, we just replace the energy by m times alpha squared and put the Hamiltonian there. So by doing this rescaling, if you substitute all these r and p into that formula, the previous Hamiltonian can be simplified. In terms of the newly defined displacement, momentum, and the Hamiltonian takes a particularly simple form as if the mass is 1 and alpha is also 1. So then we can deal with this simpler problem. Because what we have learned from there also apply to the more general case. You just need to restore all the units by putting in this coefficient again. For example, if we compute what is the energy level of this system, then we can just multiply that energy level by this constant, then that will be the true energy of the original system, something like that. So it's not a big deal. And by doing this kind of rescaling, I think we have used the similar idea of rescaling momentum and position in harmonic oscillator as well. And there we also use this trick to get rid of all these unwanted factors. And then this rescaling is such that you can see it preserves the commutation relation. Because previously, displacement and momentum has a commutation relation that is x times p minus p times x equals identity times delta function of its components. And then if you rescale it in this way, you will see that the commutator doesn't change. So it's very, very nice that we are using a rescaling which preserves commutation, but we simplify our Hamiltonian. So in the end, the Hamiltonian will be measured in terms of this energy unit. So this Hamiltonian is dimensionless now. But if you want to restore the energy, then the energy unit is basically something like m alpha squared. And people sometimes always divide it by 2 because for historical reason, this energy unit actually is first defined as the so-called Rydberg unit of energy, which arises when people study hydrogen atoms. It is actually the ground state energy of the hydrogen atom. Okay, so now that's from now on we will focus on this dimensionless problem, where Hamiltonian take a particularly simple form. It contains a kinetic energy term which proportional to p squared and the potential energy term which is minus 1 over r. So in classical mechanics, what we can do is we can compute the time evolution of position and momentum, because in classical mechanics, we don't worry about that they don't commute and then we cannot measure them simultaneously. We just treat them as classical variables. So the classical equation of motion is given by this equation. This is also called the Hamiltonian equation. If you want to know what's the time derivative of position, you take a partial derivative of your Hamiltonian with respect to momentum. And the time derivative momentum is determined by the partial derivative of Hamiltonian with respect to position with a minus sign. So if you use this principle and then substitute this Hamiltonian, you will get this equation. It makes a lot of sense. The momentum is proportional to velocity, because mass is 1 now. And then the momentum, time derivative of momentum is actually the force, and the force that is experienced by the particle, which is the electron here, will be like inversely proportional to the square of the distance and along the direction that is pointing towards the proton. Okay, so these are things that we already know. And then by solving this differential equation, you can see that electron will orbit the proton in classical mechanics in an elliptic orbital. So that's the conclusion. And then in this problem, there's a nice thing that is this Hamiltonian is rotation symmetric. Because if you try to rotate your frame of reference, p squared doesn't change because p squared doesn't care what's the direction of p. And then this r, which is the distance, which is the length of the displacement vector, also doesn't care what's the direction of the displacement. So if you rotate the whole system, although both the r vector and the p vector will rotate by the same angle, but eventually it doesn't change the Hamiltonian, so the Hamiltonian has a rotation symmetry. And because the Hamiltonian has a rotational symmetry, this symmetry enforces that there is some conserved quantity associated with this symmetry, which is the angular momentum. And angular momentum in this system is defined as the cross product between displacement and momentum. And it can be checked that the angular momentum is actually conserved. The way to check it is directly just substitute this equation of motion into this time derivative of angular momentum, because if you take the time derivative on the left-hand side, using the product rule, the time derivative goes to the derivative of r cross p and plus the r cross the derivative of p. Basically, the derivative, time derivative of r and time derivative of p, you can know what's the result there, and if you substitute everything in, and I think it's not difficult to check that angular momentum is indeed conserved. That means it doesn't have any time derivative. So that is an obvious conserved quantity associated with the symmetry. Well, the symmetry here is SO3 rotation symmetry. The name of SO3 means the special orthogonal group of dimension 3, which means it's a 3 by 3 matrix, orthogonal matrix, which implements the rotation. The reason that the rotation is always implemented by orthogonal matrix is because in this classical mechanics, all the vector is a 3-component real vector, right? And then if you want to, what we mean by rotation is that you want to change the direction of the vector without changing the norm of the vector. So for example, if you have a displacement vector, and then I want to do a rotation and take it to a new vector, r prime, and by saying that it is a rotation, that means it must satisfy a condition that the norm of the vector, which is given by r dot r, of course, the length of the vector is square root of this guy, but doesn't matter. By preserving the length of the vector, we mean that you need to do something like that. But if you suppose this new vector is related to the old vector by some matrix, this vector is a 3-component vector, 3-dimensional vector. And then so this O is basically a 3 times 3 matrix in order such that 3 times 3 matrix times a 3-component vector can give you a new 3-component vector, right? But now you can use this idea that this R dot, suppose you have O transpose here and then O and then R. So if you dot this vector and matrix and vector together, that basically means that if you, so there's no prime here. So if you want to preserve the norm of the vector, this O transpose O must behave like an identity matrix. So that's the definition of orthogonal matrix. So orthogonal matrix is basically defined to be any matrix which any real matrix such that every matrix element is a real number, but the matrix itself is a square matrix, and then matrix times its transpose is identity. In comparison, unitary matrix is like that, right? So unitary matrix element is a complex number. And then because for complex number, you cannot just transpose, you just need to do transpose followed by complex conjugation. So this is the unitary matrix. and this is orthogonal matrix. So when we talk about rotation in real space, so you use orthogonal matrix because you rotate the real vector, the resulting vector still must be real. You cannot use a complex matrix to do the rotation, right? So the matrix must be real, meaning that every matrix element is real. But in order to preserve the norm, the matrix not only need to be real, but also need to satisfy this orthogonal condition. So that's what we mean by SO3. Okay, it's a 3 by 3 orthogonal matrix. Any matrix satisfying this condition, and it's real. And the word special simply means another condition, which is the determinant of this matrix is 1. Why is that important? Because there are also some transformation. For example, if you flip x direction to minus x direction and keep y and z direction unchanged, that's also an orthogonal transformation, but that's not special. That kind of transformation has a determinant -1. So special orthogonal transformation basically means any norm-preserving transformation of 3-dimensional vectors, which also doesn't flip the orientation, like doesn't do a reflection. So this kind of orthogonal transformation excluding reflection is basically SO3, which is actually all the rotations. Yeah, that's trying to explain this terminology. Okay, so far so good. So I think these are all we have learned previously, but people didn't, maybe you didn't realize, and actually it's also for people to take a long time to realize that actually there's a hidden symmetry in the problem. This is because there's another conserved quantity which we don't usually talk about. And this new conserved quantity, which is also there in this dynamical system, and then it's very difficult to discover because it has a very complicated expression. But this vector has a name called the Laplace-Runge-Lenz vector, discovered by these 3 physicists. And then long times ago, of course, when quantum mechanics was not there yet, they discovered this in classical mechanics. So this vector is also denoted as A. Its expression is basically given by the momentum cross product with the angular momentum minus displacement over the distance. Okay, so it's a very complicated expression. In order to show that it's a conserved quantity, I try to make an animation. So this A vector, as a vector, it has a direction and also angle, for example. So the direction of this A vector is basically, let's say, if it is along the x direction. And then the length of this A vector, I have a slide bar here, which I can tune. So if we always put the A vector along this x direction, then if you change the length of the A vector, actually that will change the shape of this orbit. We know that if you have this inverse square law force kind of problem, like the Kepler orbital, the orbital will also always be a elliptic. It will always be a ellipsis, and then the one of the force center will be at one of the focus points, basically. So you can think of the electron is here, the proton is here, and if the electron is moving on this orbital, what happens is that it is changing the angle theta, basically. So you can use this angle theta to parameterize. If we change the angle theta, that is like the electron is moving along this orbital. You can see it's moving. But as it is moving along the orbital, what happens is that you can at every point, you can compute, first of all, P cross L. L is the angular momentum. Suppose the electron is circulating in this direction, then L is pointing out. And then maybe P is maybe circulating in this direction. Then L is pointing in, and then P is, I think in this case, is going along this direction. Then P cross L must always be a vector which is perpendicular to momentum, which is along this direction, also perpendicular to angular momentum, which is pointing either outwards or inwards, depending on along which direction it rotates. And then, so the only direction that is perpendicular to both of the tangent direction, and this outward direction is this direction, which is basically perpendicular to this tangent and lying in the plane. So we know P cross L must be a vector along this direction. And the length of this vector, we know this L vector is a conserved quantity, so its length doesn't change. But the P vector can change its length, because the P vector, if you move towards, if you move to somewhere here, then the momentum will be very large, because at these points, the electron will be moving very fast. I'm talking about classical electron, or you can think of it as a planet. But if the planet is very far away from the sun, for example, in that point, then this planet will move slowly and its momentum will be small. So you can see that the momentum actually sometimes is small and sometimes is large, and also it changes directions. So this blue vector it's not a conserved vector. But we also have this green vector, which is the second term. The green vector is always the unit vector along the displacement direction, because it's basically the displacement vector divided by its norm, so it becomes the unit vector. So that's why I put a hat here. This hat doesn't mean it's an operator. This hat just means that this is a unit vector. But magically, although this unit vector is also changing its direction, and this P cross L is also changing its direction as well as its length, but the difference between this blue vector and the green vector, which is the first term and the second term, if you take a difference, the difference, which is the red vector, never change. So, there's an underlying program that is calculating P and L and R all the time. And then you can trust this mathematical program, and then it shows that this A vector never changes as the electron is orbiting surrounding the proton. And this A vector, you can also parallel transport it to this focus point and then draw it here. Then that corresponds to basically a conserved vector. And you can actually show that this vector is a conserved quantity by using the time derivative. So you can take the time derivative of this vector given this definition. So don't ask me how do people magically figure out this vector, but it is a fact that if you take the time derivative and then you can time derivative over P, time derivative over R, and then finish all the calculus, and then it can be checked that this A vector is indeed also a conserved quantity. And the physical meaning of this A vector, I want to talk about the meaning of the A vector. It's basically the direction of this vector tells you along which direction is the longer axis. There's a major X for the elliptics. And then there's also a, I think I explained here. So, yeah. So this conservation law is useful in solving this Kepler orbital, and then that theta be the angle between R and A, let's say. So if A is a conserved quantity, basically we can come up with a conclusion that A dot R. So A dot R is always like this, and then that means A is a conserved quantity, so we can always split its, it's like a stationary vector, so we can parameterize any displacement by the angle with respect to the A vector, and then also take out the length of the A vector. So we know this quantity must be equal to this guy. So now if we're plugging into the so-called scalar triple product, that we can simplify the first expression. The first expression out there basically can be rewritten as L dot P cross R, which is L squared. So that basically means this quantity is L squared minus R. So that's why we can solve from this equation that R basically equals L squared over 1 plus A times cosine theta. So we can solve this R out of this equation. Because L squared is a conserved quantity, so it doesn't change. And because A is also a conserved quantity, it doesn't change. So this gives us an expression of how does R depend on theta. But in this way, if R depends on theta in this way, if you draw it, it will be an elliptical orbit. And then this orbit will have this A and C. So what's this A? A is like the half length of the major axis, and then b is the half length of the minor axis, and c is the distance to the focus point. So it's like that. So in geometry, we know there's a relation between a, b, and c for ellipse, and then it's like b squared plus c squared is a squared. So using this orbital equation above, we can also infer what is a, what is c, and then it's given by these expressions. So you can see that this a LRL vector, its direction basically sets the direction of the major axis, and then its length basically sets basically the shape, what's the shape of this, sometimes also called eccentricity of the orbit. So the magnitude is actually conserved because the eccentricity of the orbit never change when the planet orbits surrounding the sun or the electron orbits surrounding the proton. And then the fact is that the C over A ratio, the C over A ratio essentially is this capital A. Okay? And then the conservation of the direction basically means that the conservation of the orientation of the orbit in the orbital plane. So the planet is moving in a plane, but in principle, if the force is not this 1 over r rule, sorry, if the potential is not 1 over r, but 1 over r to the, for example, 1.2 power, then it doesn't have this conserved quantity. Then in that case, the orbit will basically change its orientation constantly. So for example, the planet or the electron will move along the in this way and keep changing its direction of major axis like that. So that is the general case if you only have conservation of angular momentum. But in this Kepler orbital, we have something more. We also conserve the direction or the orientation of the orbit, which is the direction of this A vector. So that's the physical meaning of this A vector in this problem, okay? So the whole discussion is just to show that there is additional conserved quantity. But whenever we see that there is a conserved quantity, we will ask a question whether there is a deeper reason, symmetry reason, behind this conserved quantity. For example, the angular momentum conservation is associated with rotation symmetry, and actually this LRL vector conservation is associated with a larger symmetry. And the larger symmetry turns out to be SO4. It's a 4-dimensional rotation symmetry. So although we are talking about this problem in a 3-dimensional space, but magically behind this dynamical problem, there's actually a 4-dimensional hidden space. And then the dynamics is actually symmetric in this 4-dimensional higher dimensional space, which is very difficult to review, but that's what we will talk about. So here is a homework, but the homework is not about this classical dynamics. It's about a warm-up of what do we mean by SO4 group. So SO4 group is a special orthogonal group of 4x4 matrices. So that means that is the set of all kinds of matrices, 4x4 matrices, which satisfy the orthogonal condition, which is like O transpose O is identity, and also satisfy the determinant equals 1 transition, but maybe that's not so important. Let's look at the orthogonal transition. The first problem is trying to show that any orthogonal matrix can be generated by a matrix A, where this matrix A is transpose anti-symmetric, and the matrix A, every matrix element belongs to purely imaginary number. This I, this I stands for the set of purely imaginary number. That is basically a real number times the imaginary unit. So this A is basically an n by n matrix where every matrix element in this A matrix is purely imaginary, and then the A matrix is also anti-symmetric. For example, this is an example of a purely imaginary. Of course, 0 is also along the imaginary axis, so it's allowed. So, and then I is a purely imaginary number. And then this matrix is only made of purely imaginary number. Of course, maybe there's also a 1/2 factor in the front, but it doesn't matter. It's still purely imaginary. And then it is also anti-symmetric, meaning that this matrix element is the negative of that matrix element. So we have some of these examples of purely imaginary this anti-symmetric matrix. But the first problem is try to show that if O satisfies this orthogonal condition and every matrix element in O is real, then this A as the generator of this orthogonal transformation must satisfy this condition. So this is just a similar idea as unitary relation between unitary and Hermitian matrix. So previously we say if you want to generate a unitary matrix, you need to e to the I theta of a Hermitian matrix. And then Hermitian matrix has a property H dagger equals H. And then unitary has a property U dagger U equals identity. So here we are going to extend it to orthogonal matrix, where orthogonal matrix is O transpose O equals identity. But then up there, it is not simply a Hermitian matrix. It's actually a purely imaginary anti-symmetric matrix. It's the property that you need. So you can try to show that these are consistent. So the way to prove that is if you first assume that this holds and try to check that by using matrix exponentiation, you can generate orthogonal matrix. Or you can check the other way around. If this is orthogonal, then this holds, given this relation. The way to do that is to expand, Taylor expand this expression, and then maybe you can consider infinitesimal rotation. Maybe that's fine. That's sufficient to show. You can just prove it either way. I think it should be fine. Yeah. Okay. So now we know that in order to generate the orthogonal transformation, we basically need anti-symmetric, purely imaginary matrices. And then how many these kind of matrices are there? Of course, there are infinite number of these matrices in principle, but all such matrices, which is 4 by 4, will be a linear superposition of these 6 different matrices. So these 6 different matrices, which I denoted as T and S, T1, T2, T3, and S1, S2, S3, actually they form a complete orthogonal basis of these A matrices, meaning that any matrix any 4 by 4 matrix that satisfies this condition, of course here n equals 4, any 4 by 4 matrix that satisfies this condition can be written as a real linear superposition of all these 4 different matrices. If you want to prove it, this second problem is trying to verify that. If you combine these 6 matrices with real coefficient, of course, it is a matrix that satisfies this condition. But the difficult thing is to prove that any matrix that satisfies this condition can be written as this linear combination of these matrices. You can think about it, how to do it. And then finally, with these expressions, we know that any orthogonal 4 by 4 orthogonal transformation will be generated by the linear combination of these generators. So these will be the fundamental generators. And these generators, just like spin operators that generates rotation, so these 6 different generators generates SO4 rotation. And these generators, just like spin operators or angular momentum operators, it also have commutation relations. And the commutation relations among them is basically like 2 sets of spins. The reason that I want to rewrite these 6 different matrices, 3 of them as T, 3 of them as S, is because these 3 S really satisfy the angular momentum the commutation relation. And the 3 T's also satisfy another set of independent set of angular momentum kind of commutation relation. And the commutator between S and T is 0, meaning that these T matrices and S matrices, they commute. And then this problem C is that you can just substitute this matrix and verify that indeed these 6 matrices, among 6 matrices, I think there are how many? 3 commutation relations, 3 commutation, and maybe another 6 commutation relations here. You can check these commutations and show that they are indeed true. So why do I want to give you this exercise? It's a warm-up exercise such that you know what is SO4, what are the generator of SO4. There are actually 6 generators. Instead of like SO3, you have 3 generators. And for SO4, you have 6 generators. And the 6 generators of SO4 forms an algebraic structure like that. So in the following, when we see the similar algebraic structure, we will be able to identify that as SO4 symmetry. So that's the goal of this homework, okay? Okay, so with that preparation, I think we can talk about SO4 symmetry. And the way to define that, again, we are going to use this operator method. So we were going to define a bunch of operators. First of all, we are going to promote all the displacement operator to Hermitian, actually any classical observables to Hermitian operator. For example, the coordinate operator or the displacement operator, which is a vector of operators. It has 3 components. Every coordinate has 3 components previously, and every component now becomes an operator in quantum mechanics. And then we can further define this distance, which as r dot r take a square root. But you can just take, you need to basically think that this R1, R2, R3 are all matrices. Although we didn't write it down explicitly, but they are operators, so operator in principle are matrices. So these are matrix squares, and then add together, and then take a square root of the matrix. Taking the square root of the matrix essentially is to first diagonalize the matrix and take the square root of the eigenvalue and then reconstruct the matrix. It's like that. So that's how you can define this R operator. We can also define the momentum operator, and then the Hamiltonian operator will be given again by just replacing every operator by its every quantity by its operator form. And then the angular momentum operator, as we previously already seen, that's basically R cross P, again, in terms of operators. So which means that every component of the angular momentum operator is given by the Levi-Civitas symbol, which is the antisymmetric, fully antisymmetric tensor, and then contracting with the components of displacement and or the coordinate and the momentum operators. And using the similar idea, one can define this LRL vector. Well, the LRL vector is a little bit, there's a little tweak here. That is, previously it's P cross L, but because P and L, they don't quite commute, so there's some ambiguity there. So the way to define it in a way that preserves the hermiticity of A, because if you just define P cross L, you can show that this way of defining, it will make this A operator non-Hermitian. But A operator as a physical observable, we wish that it can be a Hermitian operator, so that's why people want to do P cross L minus L cross P. It's like in classical mechanics, P cross L and L cross P will just be differed by a minus sign. So essentially, these two are the same thing. And then if you take a 1/2 of the sum of these two, it's like taking an average of P cross L and minus L cross P, right? But in quantum mechanics, because some non-commutativity between these operators, so it's necessary to do this kind of a symmetrization and then or Hermitianization in order to make this A operator Hermitian. So A operator will be defined in this way. I'm just going to show you how things are defined. And don't worry about the calculation, because I know this calculation is very complicated, and then it will not appear in any exam. I just want to show you this algebra. Okay, so with all this definition, now we are ready to compute the operator algebra. So we will start from the commutation relation between coordinate and momentum, which is defined in this way, that the coordinate and momentum, if they are along the same direction, if they are both x direction, then there's a non-trivial commutation relation, which is I times identity. But if it's along different direction, for example, the x direction coordinate and y direction momentum, then they simply commute because they correspond to motions in different directions. So that's the basic commutation relation between coordinate and momentum. Using that and using all the definitions that we have listed above for the angular momentum, for the LRL vector, and for the Hamiltonian, you can basically check all these commutation relations. For example, the first equation says that the Hamiltonian commutes with L and also commutes with this LRL vector, which means L is a conserved quantity. Because remember, if you still remember the Heisenberg equation of motion, that if you have any operator, the time derivative of this operator is basically given by the commutator of Hamiltonian and that operator, something like that. So if Hamiltonian and the operator commute, that means this operator has no time derivative. Any questions? Okay, any operator that commutes with Hamiltonian is a conserved quantity. So these two expressions shows that these two operators indeed are conserved quantities in quantum mechanics as well. But these conserved quantities, they have algebraic relation. For example, L and L has a commutation like that, which is indeed the angular momentum kind of commutation relation, right? But if you take a look at A and A, well, it doesn't look so good, because A and A, if you calculate its commutator, it goes to L times H, basically. It doesn't go back to itself. And L and A also has non-trivial commutation relation that goes to A. So it has a pretty complicated commutation relation. And then one can try to verify all this. How do I verify all this? Actually, it's very difficult to verify this by hand, because the definition of this operator are so complicated. So the strategy is to write a computer program. So if you are curious, you can take a look at this exercise. We really use Mathematica to construct an algebraic system. It's very nice for Mathematica. You can define your own symbols. For example, what do you mean by cross-cross, right? You can define something like that. You can also define what does it mean by commutation relations. Then you can check, you can use these rules. You can just type in all the basic rules of algebra, and then you can try to verify these rules holds for simple examples. Now, using all these rules, you can start to define operators, and then you can try to compute. For example, you can compute applying these rules to these operators, whether that holds. For example, commutator of p squared and R3, it will become minus 2i times p3. It will give you the result. So this computer system is pretty powerful that it allows us to eventually check all these relations one by one. So I did all that check there, end of exercise 30. So it's a very long exercise and contains a lot of programs. The point is that previously we think that when we do analytic physics, like when we do theoretical physics, we need to sit down with a pen and paper and derive all the formula by human intelligence. But in the future, actually nowadays, we can already use computers to do algebra, to derive equations for you. So we can check all these equations using computer. It's very I think it takes human like half a day to check all these expressions, but takes computer maybe 2 seconds. So it's very convenient to use that. And then one can also check that there's some additional relations that these, for example, A dot L and L dot A equals 0, and then which means A and L are always orthogonal to each other, which is true because A is lying in the orbital plane, this LRL vector, but the angular momentum is perpendicular to the orbital plane, right? So no matter which direction that this A lies, it must be perpendicular to the angular momentum operator. So that's why this operator equation also holds, and you also have another equation like that. So with all these algebraic relations, yes, I have some comments here. So for example, these basically means L and A are conserved quantities. So one might expect that L and A will generate a symmetry group. However, this expectation is not true because the algebra, the commutation relation, this kind of algebra relation is not closed. In particular, A and A commutator leads to new operator like L times H. Because if you want to say that these two operators forms an algebra, that means if they commute with each other, if you calculate any commutator among them, it must be decomposed into linear combination of this L and A. But that's not true because A and A commutator goes to a new operator which can never be written as a linear combination of L and A, so that's not a closed algebra. So that's why the algebra must be further extended. But then there will be more complicated. But maybe we don't need to do that because if we can restrict, because you can see this algebra is almost closed. The only thing that make it a new operator is that this H, this Hamiltonian, is not a simple number, it's an operator. But suppose we can restrict ourselves within each eigen subspace of this H. meaning that we only talk about those eigenstates of the same eigenvalue that form a subspace of H. In that subspace, H effectively reduced to a number which is the eigenvalue of this Hamiltonian operator. So in that case, if every time we only consider one energy level and consider the degenerate state within that energy level, for that reduced problem, this H is only a number. And in that case, the AA commutator is just can be written as L with a coefficient in the with a multiplicative coefficient, a scalar coefficient. So in that way, the algebra closes. And when the algebra closes, we can actually form the symmetry group or the Lie algebra. So the way to define is basically you can redefine. Suppose the Hamiltonian has an energy, eigenenergy, which is denoted as E, which is less than 0. Then you can replace every Hamiltonian operator by its eigenvalue, and then we can define a new LRL normalized rescale LRL vector, which is the original LRL vector divided by some kind of energy. The reason to do that is by doing this, by defining this new rescaled LRL vector, we can find that its commutation relation is somewhat more clean, right? We don't have all this H hanging around in this case. So it has a nicer property. So with this property, now we can define, T and S. And it's amazing that people figure out all these steps and then keep defining things. And then eventually, gradually, this SO4 algebra will emerge. So you further take L and N. L is the angular momentum. N is the LR vector, but normalized by the square root of the energy. But because energy is still a conserved quantity, LR vector is a conserved quantity, so N is also a conserved quantity. L is also a conserved quantity. So the summation divided by 2 is also a conserved quantity. T is also a conserved quantity. S is the difference divided by 2 is also a conserved quantity. But by defining all this, and finally the SO4 algebra finally emerges. That is what we have done in the homework 4. That is T and S indeed satisfy the SO4 group algebra. Okay, so that's why people discover or prove that actually the problem has a SO4 symmetry, because your Hamiltonian will not now the Hamiltonian commutes with all the T and S, and T and S each forms an angular momentum algebra, and they combine together forms a SO4 algebra. And this SO4 group basically says that you can now use the eigenstates and eigenvectors or the quantum numbers of T and S to label every eigenstate of the Hamiltonian. Maybe we will do that next time. But yes, questions?
Right, I was just wondering, so we have TA and SB becoming here too, but what about SA and TB? Would that also be 0, or would that be something else?
Yeah. That's a very good question, because if you know TA and SB, and then you know that the commutator of SB and TA will just be the minus sign of this commutator, right? Any operator A and B commutator is AB minus BA. Remember this definition. So if you exchange the operator in the commutator, what happens is if you exchange A and B, you get a minus sign. So if you exchange these two operators, you get a minus sign. So now if this is 0, then this is also 0. If this is 0, because I haven't specified what's A and B, so I can rename B as A as B. So that means this is also 0.
Okay. So
yeah.
If we had TB SA, that would still be 0?
Yeah, if we have SA TB, that will also be 0. That's why we don't need to write the fourth equation again, because the fourth equation and the third equation is the same equation. It's related by the definition. So we basically finished giving all the homework, so there will be no more homework for the rest of the quarter. I know some of you have been very actively doing all the homework, but some of you very reluctant to hand in the homework. The point is that try to hand in the homework, because maybe I didn't announce that you have infinite chance to resubmit the homework. So don't think that you hand in the homework and then get graded and then lose your point. No worry for that. If you didn't do it correct the first time, you can resubmit and then we will regrade. So you can resubmit until you are satisfied with your grade. So that's the policy for the homework. So take advantage of that policy and submit your homework in time. Yeah. Okay, that's it for today. Thank you.
Here I was going through notes and I was a bit lost. So I was going through that part of the first